At a speed of about 100 miles per hour, a small aircraft generates enough lift to leave the ground and climb into the sky. A Formula One car regularly travels at double that speed, yet instead of taking flight, it becomes more firmly planted to the track. This is the central paradox of F1 engineering. These machines are not designed to move through the air, they are designed to manipulate it. Every surface, from the front wing to the rear diffuser, is a calculated attempt to turn the atmosphere into a physical weight. To understand how this works, we have to look at the profile of an aerofoil, or wing. On a commercial airplane, the wing is curved on the top, forcing air to travel faster over the upper surface. According to Bernoulli's principle, faster-moving air has lower pressure. This pressure difference creates lift. An F1 car uses this exact logic, but in reverse. By flipping the wing geometry upside down, engineers create high pressure on top of the car and low pressure underneath it. The atmosphere effectively pushes the car into the pavement. In the early days of Grand Prix racing, cars were shaped like cigars. They were sleek and fast, but they were also aerodynamic nightmares. As speeds increased in the 1960s, these cars began to behave like wings themselves, lifting off the ground at high speeds and becoming terrifyingly unstable. It wasn't until engineers began experimenting with inverted wings that the sport truly changed. This stiffest at the end of the era where cars were merely fast, and the beginning of the era where they became slaves of the air. The most powerful tool in an engineer's arsenal isn't actually a wing you can see from the outside, it is the floor of the car. This is known as the ground effect. By shaping the underside of the car into long, hollow channels called venturi tunnels, engineers can accelerate the air passing beneath the chassis. This creates a massive zone of low pressure that literally sucks the car toward the track. The closer the car is to the ground, the more intense this suction becomes, creating a physical bond between the carbon fiber and the asphalt. In 1978, designer Gordon Murray took this concept to its logical, if extreme, conclusion with the Brabham BT46B, better known as the fan car. Rather than relying on the car's forward motion to create a vacuum, Murray placed a large fan at the rear of the car. This fan actively sucked air from beneath the chassis, creating immense downforce even when the car was standing still. It won its first and only race so convincingly that it was immediately withdrawn under pressure from other teams, but it proved just how powerful suction could be. Modern F1 aerodynamics are not just about creating downforce, they are about managing dirty air. When air passes over a car, it leaves a chaotic, turbulent wake behind it. This turbulence makes it difficult for a following car to generate its own downforce, preventing close racing. The 2022 regulation changes completely redesigned the cars to solve this. By using the ground effect tunnels to throw the turbulent air high into the sky, engineers have allowed following cars to stay closer in the corners, turning the air from a barrier into a shared resource. At the front of the car, the front wing acts as the first point of contact with the air. Its job is twofold. It generates a small portion of the car's downforce, but more importantly, it conditions the air for the rest of the bodywork. It creates vortices, spinning spirals of air that act like invisible curtains. These curtains help seal the low-pressure area under the floor, preventing outside air from leaking in and ruining the suction. It is a delicate balance where a single millimeter of adjustment can change the entire car's performance. Downforce, however, comes at a cost called drag. The more a wing pushes the car down, the more it resists forward motion. This is why F1 cars use DRS, or the drag reduction system. On long straights, the driver can flip a switch to open a flap on the rear wing. This reduces the wing's surface area, shedding downforce and drag simultaneously. It allows the car to gain an extra 10 to 12 kilometers per hour, essentially transforming the car from a high-grip machine into a low-resistance projectile for a few brief seconds. The sheer scale of this force is difficult to visualize. At top speed, a modern Formula One car generates roughly 750 kilograms of downforce, which is more than the car actually weighs. In theory, if you could build a tunnel with a perfectly flat ceiling and drive an F1 car at 150 miles per hour, the suction would be strong enough to overcome gravity. The car would stay pinned to the ceiling, driving upside down without falling. It is a testament to engineering that these cars are more at home on a ceiling than in the air. The future of this science lies in active aero. While current cars are mostly static, The 2026 regulations will introduce wings that change shape in real time during a lap. This will allow cars to have maximum grip in the corners and minimum drag on the straights automatically. We are moving toward a future where the car is a living, breathing organism that constantly reshapes itself to cheat the laws of physics. It is the ultimate evolution of the battle between air and carbon fiber, a pursuit of speed that never truly ends.
If you'd like more videos like this, you can subscribe and come back to Brief Stories anytime.